Hello everyone. We feel very sorry that we cannot attend the conference in person due to the complicated situation of the coronavirus. But I still feel very glad to present our job here. I am Bangwen Deng from Tsinghua University, and this is a joint work with my advisor Wenfei Wu and Professor Linhai Song in Penn State University. Today I want to talk about the redundant logic elimination in network functions. As we all know, as SDN and NFV develops, software network functions have growing impacts in nowadays network. We can find diverse functions in various network scenarios. Network functions process all traversing traffic in the data plane, so their efficiency affects the whole network's end-to-end performance. However, during NF development, developers might try to cover a large protocol space in the program for completeness, while in the runtime deployment, NF operator might only configure a subspace of the entire protocol space. The mismatch of the protocol space in the development and that in the deployment leads to redundant logic. Our goal is to use compiler techniques to optimize away the redundancy caused by the mismatch. We first use examples to show our design intuitions. Here we show the simplified SNOT IDS code. As a rule-based intrusion detection system, SNOT first loads the configured rules and then executes the packet processing loop. When a packet comes in, the loop first parses it and then conducts rules matching. If a rule is matched, the corresponding action will be taken. As you can see, the packet processing is layered. From the SNOT code, we observe the first type of redundancy that all on-off logic designed for a protocol layer may be redundant. For example, if only layer 3 header is used, and all rules use wildcard to match any port numbers, the incoming packet port number always matches all configured rules. Then the packet port parsing operations are useless and should be redundant. To eliminate it, we can first load the configs into the program, and then do constant folding and propagation, and finally eliminate the redundancy by data code elimination. We also observe the second redundant type that the logic for a protocol may be redundant. For example, if the NF is configured to process TCP packets only, all UDP packets will be ignored. Then the UDP packets parsing operations are useless and should be redundant. For this case, we can extract the feasible paths first, and for each feasible path, we perform constant folding and data code elimination to remove the redundancy. The first two types are the intra-NF redundancy. We describe cross-NF redundancy as type 3. The computation of a previous NF may be redundant due to the configured rules of the latter. For example, if a monitor deployed before an IDS instance who block UDP packets, all the parsing and counting for the UDP packets in the monitor is redundant. To eliminate the third type redundancy, we can consolidate the two NFs into one program first, and then apply type 1 and type 2 redundancy elimination on it. Finally, we decompose them back. Let's look into the implementation of NF reducer. NF reducer contains 4 parts. It takes the network function source code and user label critical variable and actions as its input. It first extracts the packet processing logic, and then refers to configurations to eliminate the intra-NF and cross-NF redundancy. NF reducer defines 3 types of critical variables. Packet variables host the packet raw data. State variables maintain the NF state, while the config variables host the configurations. Packets and state variables are important to identify the NF actions, while config variables are the key to eliminate the redundancy. NF reducer also defines 2 types of NF actions. External actions denote the action processing the packet, while internal actions managing the NF state. Current labeling job is operator involved, and we will automate it in the future. Next, NF Reducer will extract the packet processing logic for two reasons. First, we want to remove functionalities unrelated to packet processing, such as log, to improve NF performance. Second, focusing on packet processing logic facilitates the compiler techniques applied later. Program slicing is the key to this process. With labeled action and critical variables used in actions, program slicer can search instructions which influences the execution of the labeled actions, and report or search the instruction as identified packet processing logic. NF Reducer takes the packet processing logic and configure rules as input to eliminate the first and second type of redundancy. As I mentioned before, NF Reducer first replaces configure variables with the constant values specified in the configure rules. Then it extracts program paths and do constant folding. Type 1 redundancy can be eliminated directly with dead code elimination. As for Type 2 redundancy, we need to filter out the infeasible paths after constant folding and propagation. Finally, we merge all the paths and get the optimized code. As for cross-NF optimization, NF Reducer applies the individual NF optimization methods on the consolidated program, and we have a preliminary discussion on the optimization of different NF chain execution models in the paper. We use an open-source static slicer called LLVNDG to do the program slicing job, and we use Kali as our symbolic execution engine, and we implement the compiler optimization methods on the LLVM platform. Let's see the evaluation part. We select two IDS, Snort and Suricata, as our benchmark. While Suricata has single-thread mode and multi-thread mode, when eliminating Type 1 redundancy, the two NFs are only configured with Layer 3 rules. In the figure, we vary the packet size in x-axis and measure the NF packet processing rate in y-axis. We can see that the performance increased by nearly 15% for Snort and by 15% to tenfold for Suricata. Suricata inspects packets deeper in payload than Snort, so its performance gain is more significant. We only configure TCP rules and regulate the UDP ratios in test chase to evaluate the effect of eliminated Type 2 redundancy. As we can see, in both NFs, the larger proportion of UDP packets, the larger performance gain we have. When the proportion of UDP packets reaches to 50%, we can get 40% performance gains for Snort and 2.5 folds for Suricata. We add the monitor before Snort instance and configure the Snort with TCP rules only to evaluate Type 3 redundancy elimination. We compare the chained NFs, consolidated NFs, and the optimized consolidated NFs. The consolidation and redundancy elimination can help improve throughput by more than 30%, and increasing the proportion of UDP packets can increase the performance gain. We conduct a preliminary evaluation on NF Reducer's overhead. First, we need user to label the critical variables and NF actions. An NF program only needs this manual labeling once. In practice, when NF configuration is changed, NF Reducer needs to be run again, which takes tens of seconds, mainly caused by symbolic execution. We think that the time is tolerable in real-world operation. In summary, in this paper, we show the existence of redundant logic in NF programs and propose a framework named NF Reducer to eliminate the redundancy. The preliminary evaluation shows that NF Reducer can improve the performance in two NFs, and in the future, we will automate the whole process further and apply NF Reducer to more NFs. We will also make complete tests on it, and that's it. Thanks very much.